Good afternoon. How's everybody doing today? Good. I'm Dan McLaughlin. I'm a lead program manager for the Windows graphics team. I've been in the computer graphics industry for over 25 years, spent a good part of it in the Bay Area here working for companies like Silicon Graphics, building graphics hardware and software. I moved up to Redmond about 7 years ago now, almost exactly to the day when I was leaving here. So it's good to be back. Let's see, for the first cycle I was the dev lead for Direct 11 for Windows 7. I then moved to the PM team and was the PM lead for Direct 3D for Windows 8. And now I'm the responsible for all of the 2D stack, so that's D-Write, D2D, imaging codecs, and all that kind of stuff for Windows 8.1. So if you got questions afterwards, I'll probably answer anything you need on any of those. It's my opportunity and my privilege today to talk to you about the innovations in high-performance 2D graphics in DirectX. So let's get started on that. So give you a little idea where we're going with the roadmap. I'm going to talk a little bit, first of all, about the performance improvements that we've done for the platform just to make everything faster. I'm going to give you a couple demos that'll show you what that looks like. And then we're going to move on to how you can actually take advantage of the new APIs that we've added into Windows 8.1 that'll actually even give you more performance. And we're going to cover three areas. That's going to be text, geometry, and imaging. So let's get started on the performance thing. So DirectX, when I talk about DirectX, DirectX is the technologies that we build into the operating system that gives you the ability to get access to the graphics hardware such that everything can be graphics hardware accelerated. And if you've watched over the last few release cycles, we've moved more and more to having the whole OS graphics accelerated, so we're getting more parallelization between the rendering performance and the CPU performance such that we're offloading things off of the CPU. Gives us better performance and better power envelope as well. So DirectX technologies are really core to all the things that we do from a graphics perspective. Internet Explorer moved on to DirectX back in IE9, and they continue to use more and more of the DirectX platform as we move forward. So give them the kind of performance that they need to be able to get access to that hardware. Office is on top of DirectX. Obviously, Windows Store, so anything any of your apps, whether they're XAML, whether they're JavaScript, are all on top of the DirectX stack, either directly or indirectly, because we power it all. So we're going to show you what we've sort of done under the covers here to make everything go more speedily. With that, I'm going to show you a couple demos. What I have up here today is I have two Surface Pros. They're identical in terms of configuration. I hope they're identically connected so that you don't give me a hard time about, oh, well, that one's DVI and that one's HDMI. So they're hooked up the same way. This one is running Windows 8. This one's running Windows 8.1. So we're going to start from there, and I'll give you a little bit of whirl through this. So that one's 8. So you might recognize this. This is the Surface commercial that was done. We did some work to actually be able to convert the images into ASCII text. So you notice how we can scale that. One thing I want to point out here, if you notice that the frame rate here, we're getting pretty much 60 frames a second. It's a lot of characters, but you notice that we're taking almost the whole frame time to do that, 16.5 milliseconds. That's about the budget for the frame. So now let's keep that number in mind. Unfortunately, I can't do side by side here, so we're just going to flip back and forth. So now this is Windows 8.1. Image is the same. Notice the frame rate. 5 milliseconds. So we went from 16 milliseconds to 5 milliseconds. What we did in the text stack is that we moved a lot of the image caching that was stored on the CPU. We moved that into the GPU and the textures. And we use the textures as a texture cache. So we're managing that directly for you. So that means that we're not pushing as much data over the network, over the pipeline to moving from the CPU to the GPU, and giving you a lot of time back to be able to have your apps take advantage of that CPU time. All right, let's go back to secondly 8. Sorry, flipping between multiples on. Don't look at this too closely. It'll probably give you a strobe effect. I don't want anybody to go pass out on me. This is an image effect that in, notice we're taking about 40 milliseconds here. So this is a test application that we did. This is running in IE directly. This is in the modern IE browser. And notice we're taking about 41 milliseconds here. This is using a lighter effect, which is one of the effects that are used. It's sort of representative of a bunch of different effects that are used to do things that are mapped into either SVG, Canvas, or CSS effects on in IE or in other browsers that implement that. So now let's look at this on Windows 8.1. Did it switch? Yes, there it is. Notice, we went from, 40 milliseconds? We're down to under 10, right? So again, we did a bunch of work into the covers, no changes in APIs. It's exactly the same code running on both surfaces. And we were able to reduce the CPU time that's required to draw exactly those same patterns. And now we're going to move on to geometry. Oops. There it is. Okay, so anybody recognize this? This is the Lorenz attractor. I'm using a stylus here to move around. Notice the frame rate here. Well, yeah, it's pretty bad. So this is probably one of the pathological cases we see. Again, you're seeing about 300, 315, 320 milliseconds a frame. So we're getting about a frame a second. Now let's flip to Windows 8.1. Show you the same thing. Did it flip? There you go. We're about 30 milliseconds, depending what it's doing. Pretty interactive. So we spent a lot of time here as well on the geometry that we do in terms of strokes to be able to get, again, the CPU time down so that we can get interactive cases running. All this is with no API changes, right? So this is just the platform getting better. So you can see across all three, text, geometry, and imaging, we've made significant investments, really listened to our developers who said, hey, these things are causing us pain. You're taking too much CPU cycles, which means I don't get to do anything in that same cycle, which means I'm half the frame rate I want to be. So we heard you, and we made investments to get the performance to a level where we think has a significant impact. When you think about text in particular, probably 80% of everything that's on the screen is text in some form or another. So anything we can do to increase the performance of text and text drawing is going to make the platform go that much more quickly. Let's see. All right. So that gives you a quick sort of overview of where we are in terms of performance and the kinds of increases that you're going to see as you move from 8 to 8.1. You're just going to get that because the platform got better. So now let's move on. And let's look at some of the new capabilities that we are introducing in 8.1 in all three of these categories. So, anybody have problems trying to draw UI elements and color emoji? Our mail team came to us and gave us a lot of hard time. This was one of their big bug farms. It's like, how do I do this? Because there's a demand to be able to show color emoji as one of the things. And it's just really hard to do. And get it right and get it to scale, especially as we see moving to higher and higher DPI devices, where if you're going to do these in bitmaps, then you have to have multiple sizes, or you're going to have to scale between them and be able to scale them up. It's a big problem. So let's look. Yeah, okay. Let's look at the way that this has been approached, and there are several different approaches to how to do colored glyphs, color UI kinds of things. The first is what the Mail app does, which is they go do analysis, and they actually look at the text strings that come in, and they say, oh, there's there's a point I want to change. They take out that particular character. They insert HTML that says insert this image, and then they have to know where that image is in their app package to be able to replace it. It's slow, it's error prone, and it's expensive both from a CPU standpoint because I have to go and analyze all the text, and it's expensive from a memory standpoint because I have to have all those glyphs around, both so on the disk and in memory to be able to do it. The second approach, which has also been done, is that the Font Foundry teams have created multiple fonts which are registered so that you say, well, I want the base level font, and you draw that. And then you say, oh, there's one that needs yellow, and then I have to go find that, and I draw that on top. And then you have to register them such that you get the colors in the right place and make sure that you get all the alignment and all the layout to be consistent. So again, it's possible, it works okay, but it's expensive and it's hard to make sure that you actually get them registered in the right place. The third that we've seen from some of our competitors is that they are promoting using embedded bitmaps into those fonts. Again, it sort of has the same kind of problems that you have from the first perspective with actually going and doing the analysis, which means the font, rather than your app, is going to be big because you're going to have to store multiple sets of bitmaps to represent all the different sizes, right? And ultimately, really, fonts are just strokes and they're outlines that we want to be able to rasterize at given frame rates. So let's talk about what our perspective is from a Microsoft standpoint. We believe that multicolored fonts needs to be a first-class citizen in the operating system, and in fact, that's exactly what we're announcing with 8.1 today. Color fonts, multiple colored fonts are supported across the platform in XAML, in JavaScript, and in DirectX. So you can turn them on, and we'll talk a little bit about how we did that. First of all, supported as multiple layer glyphs, so these are defined just like you define any other of the way you define a glyph in a font. They're multiple layers, which means that they're Z-ordered, so you say this is the bottom one, this is the next one, this one, next one, and then the operating system takes care of drawing them in the right place for you so that they're registered correctly. We did this by extending our OpenType implementation of the OpenType font specification by adding two new tables, which is, one is the color table, which basically specifies a list of the glyphs that are tied with that base glyph for each of the color layers in the Z order. And the second is a color table, is a color palette, and that palette specifies the different colors for different ranges. But it's still text, right? It's drawn the same way text works. So that means if you have applications that are using fonts today, and you turn on color fonts, your printing is still going to work. Everything else is going to work the same way because it's just integrated into the operating system. Finally, we're actually releasing a new font as well that's in the Sego UI family. It's called Sego UI Emoji, and this supports the most commonly used range of the emoji character code points that are in use today. So again, you can pick this up and you can play around with it with the 8.1 build that's released today. So with that, let me show you what this looks like, because it's more fun to do that than just talk about it. Here we go. So here's an example. These are some of the code points that we have in the, see that they scale nicely, whether we scale them really big or we shrink them down. So we've also spent some time, we have a font team up in Redmond who has been working with some of our font foundries that got glyph outlines, and actually took those glyph outlines, the font foundries that do the multiple fonts, right, the multiple layers for fonts, and we converted those into this new representation, basically took those outlines. So I'm just going to flip through these kind of quickly so you can see some examples of how this might be used. Dingbats, so you can think about these as UI elements as well. And they're glyphs like anything else, right? So we can scale them and move them around. So the other thing I want to show you is we also did that same team did some work looking at UI elements, because this really opens up the ability to be able to say, well, if I have now a way to be able to represent strokes and have those strokes be available to me such that I can use them on my UI elements. And actually, if you look at the bar at the bottom, this is the bar is done in XAML, and I actually just turned on colors so you can see that the glyphs are actually, those are also UI elements as well. So we played around a little bit with taking some of the Office assets, which are in bitmaps, and converting them into the same form, and you can see how that really gives us a lot more scalability. So you can think about it from a standpoint of, well, if I have them in a font, then I don't have to think about, well, I need to have images or bitmaps for 100%, 120%, 180%, 200%, right? So think about all those different DPI levels that you're going to get. And we see devices coming now that are 300 plus DPI. There's some that are going to be 400 on the market, right? And when you think about those and you want images to look nice and crisp, the font system is well tuned to be able to draw glyphs very quickly, as you saw from the performance we've already shown you. So I'm sure you're wondering, well, okay, if I'm using DirectX, how the heck do I turn these on? Well, it's really pretty simple. If you're using text layout with D2D, all you need to do is turn on that bit in there, and you've got color turned on. If you're using draw glyph runs, which a lot of apps use, if you're doing your own kind of layout, you're going to get the glyphs back from DWrite, where you would say draw glyph run instead, and this is kind of in pseudocode. You're going to actually query to translate that into an iterator. That iterator then gets used, and you iterate over those colors and draw the glyphs. This is why it just works, right? We didn't change any of the drawing APIs to be able to do color fonts. It just works. It also is on by default in XAML. It's also on in default with JavaScript and HTML. All right. So that was text. Let's move on and let's talk a little bit about geometry as the sort of the second leg of the stool when we think about all the things that we do from a 2D perspective. 2D geometry and geometry performance. This is another place, as you saw when we looked at strokes, which was a place that we heard a lot of feedback that geometry really isn't as fast as it needs to be. And part of that is complex geometry is CPU bound. So it's like, how do we get out of that CPU cycle such that we can push stuff to the GPU faster and let the GPU work? Part of the challenge is that graphics hardware likes to think in triangles, and 2D geometry doesn't think in triangles. It thinks in nice smooth curves and surfaces and stuff like that. So D2D has to do a whole lot of work to figure out what triangles it has to draw to the hardware to get it there, right? So that's one of the big challenges. The existing optimization techniques that we've talked about over the last few build conferences have their limitations, especially as we start to look at higher and higher DPI systems where we're talking about, well, generate bitmaps or generate masks and then use the brushing techniques to do that. Well, at higher and higher DPIs, you're going to start to see that it really isn't robust. When you think about rotations, you're going to have to regenerate them. Scaling doesn't always necessarily work and starts to get jaggies as well. Bitmaps also consume some significant resources, especially when you think about the higher DPI systems. The other one that we've talked about some is the geometry meshes. The limitation with geometry meshes is that it really, from a rendering perspective with D2D, only has aliased rendering available, which means if you really want to get high quality anti-aliasing, which is really what most 2D applications really want to see, then this is a limitation as well. So there's two solutions. If you have 11.1 hardware, there's actually hardware support. There we go. 11.1 hardware, we actually utilize that hardware. There's a feature in 11.1 hardware called TIR, which allows us to be able to do a lot of the anti-aliasing and rasterization more easily using that hardware. In 8.1, we're actually also using the tesselators, which are in the 11 hardware, to be able to offload more of that CPU cost to the GPU. There's one caveat here. You need to use the fill mode alternate if you want to get the best utilization of that hardware. That's because the tesselators don't like the other mode very well. And so we have to fall back for CPU for tessellation, but we can still take advantage of TAR. So look at that. Actually, at the end of the deck, if you go, and these will be available afterwards online, there's links to actually go look at this. There's a great MSDN article that talks about the different winding rules. Note, if you have simple geometry that's not self-intersecting, then it doesn't really matter, because it's really when they start to get loopy that we have problems in terms of that the fill mode actually kicks in. The second is, with Windows 8.1, we're introducing a new geometry called geometry realizations. And so let's talk a little bit more about what that's all about. So geometry realizations, this is a new class within D2D. And really what we're doing with geometry realizations is we're allowing you to be able to amortize the cost. So in typical geometry rendering, every frame we're going to go figure out how we have to tessellate that piece of geometry to make it look nice and smooth the way you want it on the screen. With geometry realizations, we can actually amortize that cost of doing that analysis over multiple frames, because what we're going to do is we're actually going to create a device-dependent representation of that geometry at a given scale factor, such that we do the tessellation once, and then you can just hand us back that handle to that geometry such that we can render it over and over again, which means that we can amortize the cost of doing that tessellation over multiple frames and get your CPU usage down as well, which again gives you more cycles on the CPU to be able to do what you want to do from your app perspective. So this minimizes our CPU resources, and it's tuned to optimize our GPU resource as well, because we're going to do this on the hardware as we're running, right? You're going to specify this command such that we know what hardware we're on, which then allows us to do the most optimal thing possible. So from a standpoint of what does this look like? In typical, when we're drawing 2D geometry, whether you're drawing it or filling it, drawing means the outlines, fill means when you're filling that with a brush. Can you move that? Yeah, okay, good. That's just that minor. When the CPU work that we do, the first thing we're going to do is we're going to do curve evaluation. So you think about it, you have a curve. We're going to piecewise tessellate that into something that looks smooth from your eye perspective, but still from the CPU or from the GPU says, oh yeah, that's piecewise continuous, and I know how to render straight lines, but I don't know how to render curves. Then we're going to tessellate that, get that into a form that we can actually render, and then we're going to push that to the GPU where the anti-aliasing and the brushing or the filling is going to occur, and you're going to get rendered geometry. With geometry realizations, what we do is we take all that CPU work, we do that once, and we represent that on the GPU. So we push that representation to the GPU, store it there. You'll have to do that once per primitive. Now there's a couple other caveats that we'll talk about in a minute about when you might need to redo that. And then on a frame-by-frame basis, all we do is say, render this geometry realization, and we're going to push that straight to the GPU. Basically, we're just going to send a command to the GPU that says, go, and then we can get back to doing what we need to do on the CPU side and let those run in parallel. So, will geometry realizations work for you? Because again, they are device dependent, so that means there are a couple things to think about. So, one of the intents here is that we want to amortize the cost of that tessellation over multiple frames. So, to make that happen, it means that your geometry needs to be thought of as static. And when I mean static, it's that its topology and its shape isn't changing on a frame-by-frame basis. So if you have something that's like blobby and moving around, on the screen, that's probably not a good idea to use geometry realizations, because it's going to be more expensive to create it and then push it to the GPU and then throw it away and then do it again on the next frame, right? But if it's static, and static doesn't mean that it doesn't change size or translation, right, or rotation. It's just that its topology is staying the same. The second is when you're applying transformations to it, scales, rotations, and translations, in particular are the scales uniform. Because if the scales are non-uniform, so if you're doing shears, you're actually doing the same thing as changing the geometry, right? Because our tessellation then isn't necessarily going to be correct such that you don't see artifacts from the fact that we are tessellating and storing it at that particular size. So the thing to think about is, how you generate the realizations really depends on what the scale factors are that you're going to apply to that geometry. So if you have a small range, it probably means that if you realize it at the highest resolution, and then you scale it down a little bit, it'll be fine. The thing you don't want to do is if you have a dynamic range that says I go from 1 to 1,000, if I realize it at 1,000 and then I go back to 1, you're going to be drawing a whole lot more geometry than you need to at a higher smoothness or resolution than you care about. If you realize it at 1 and then scale it up to 1,000, well, the illusion that it's smooth isn't going to be there. So let me show you what I mean by this. This is a piece of sample code that's actually available in MSDN. It should be available today. It was released today. And this shows how to use it. Now, this particular version we tweaked to be able to show you this. This actually does dynamic scaling such that when the scale factor changes by more than a factor of 2 geometrically, it actually re-realizes. And you can see that code and how we do it. What we did is actually tweak this so that you can see if I have the wrong scale factors, I break the illusion, right, of being able to make it smooth, because it's supposed to look like this, right? But if I scaled up and didn't re-realize, then I break the illusion that that's actually a smooth curve. All right, so that was geometry. So that was the second of the the three. Now let's move on to imaging, and I'm actually going to cover 2 different areas within the imaging area. First of all, in Windows 8, we introduced a new concept within Direct2D called the image effects pipeline. And as people started to use it, and as developers used it, and we started to get feedback, we realized that there were certain characteristics of this that ways of usage patterns that were better to optimize, and there were ones that were really hard to optimize such that we were seeing performance bottlenecks. We spent a bunch of time, as you saw in the demo at the very beginning, about improving performance of image effects in general. But there are some things that can be pitfalls if you're not careful. So the first is, you want to think about when you're running an image effects pipeline, and for those of you who aren't familiar with the image effects pipeline does, it basically allows you to be able to specify a series of transformations that doesn't have to be just a straight line. So you could say these things come together and then branch apart and come back together. And you define that up front, and then you can provide inputs and run it through. The other thing about image effects is that it actually allows you to defer that rendering such that you don't have to evaluate the whole image if what the output is only a small portion of it. So we do a bunch of work to work back through that and determine exactly the areas of the image that needs to be applied to get you the final effect. The challenge is you want to make sure that you defer any rasterization that you do as long as possible when you're actually generating the images along the way. Example. In IE, when you think about the DOM, which is the definition of what the whole page looks like, if you have a video over here and you've got text over here, and the way that they go through that analysis is that they may say, oh, this little section over here, I'm going to realize that first, and then I'm going to go over here and realize this, and then maybe CSS applies some transformation on it later, and that invokes an image effect. Well, if they render that here and they render it here, you're going to do the full rendering of that, because even though the whole thing may not be needed in the effects pipeline. So defer that, and one of the ways to do that is actually to use command lists, right? And we basically promoted in the past that command lists were the best thing. The place to use command lists were actually to do them for printing, right? Run to command list and then send that off to the printer, send the command list to the printer, rather than rasterizing first. Well, command lists actually have more utility than just for printing. And here's one of the examples. If I'm doing a bunch of geometry and then I'm going to apply some effects to that geometry, think about if you're going to do a complex set of buttons and you want to do a drop shadow and maybe you want to do some blurriness and you want to do things like that to it. When you do that, if you use that to a command list, it then allows us to say, oh, we only need these sections of it. We'll only rasterize those sections that we need when we do the analysis. But if you did it up front, then you already spent that. I can't do anything about that if you say, Dan, go render this. Okay, I'll go render it, right? But maybe I don't need all of it. So defer that as much as possible. That allows the runtime to be able to do the things necessary and get you the best performance possible. Again, so what you want to do is avoid just rendering once to that bitmap and then sending it off. Now, on the other hand, if you're using that in multiple places in an image effect pipeline, think about, I want to do a drop shadow, so maybe I'm applying that in one place, but then I have another path through, so I have one here and both going in. Then if you render those once and apply it in multiple places, that's more efficient than using a command list, because then we have to render it twice. So it's kind of mix and match, but it's thinking about making sure that you're not doing extra work by minimizing that redundancy. So use render target bitmaps, so that's kind of the opposite of saying don't use them. If you're only going to use them once, think about deferring them. If you're going to use them multiple times, right, if they're input in multiple places, then use a bitmap. You can consider command lists here in some cases. I know it's kind of wishy-washy in terms of a clear statement, but it's because image effects are so flexible that it's hard to say, do this always, because there'll be cases where it's like, yeah, but not there. So you just need to think about, how am I using that data and where are the places that I use it, such that I can make sure that I'm minimizing the amount of redundancy that we're doing, and let us do the hard work of trying to do the right shuffling to make that fast. So that was image effects. Now I want to talk a little bit about compression. And in particular, I want you to think with me about what happens in our applications with regards to images, especially as we start to think about higher DPI, higher screen sizes, 3K by 2K. That's a lot of real estate, right? And if you want your backgrounds and you want your images to be high quality, then you need to think about how much memory you're actually using, because they're going to consume a lot of those resources. And what we see is that images are a significant portion of the both startup times, from the standpoint of loading those images if they're high big sizes, and also the utilization of the memory that you actually have in your app. Now remember, one of the reasons that you want to kind of reduce that is that as users swipe away or move to another app and then come back, if there's too much memory, if there's memory pressure, your app is going to get paged out. Where if your app is smaller, your app is going to stay in memory, which means it's going to come back when the user comes back to you more quickly. The second is to think about the quality versus space trade-offs. If you think about JPEG as an example, right, there's quality knobs that say, well, I can get better compression, but it may be a little grainier, or I can get better image quality, but it's going to be a little bigger. So you need to think about using those dials as ways to control that as well. So one of the things that we're introducing again with 8.1 is Direct2D now has support for 2 native image compressed formats. So up to this point, Direct2D always used RGBA bitmaps. That means everything had to get into a fully realized size before we could do anything with it. So the first is let's look at JPEG as an example. JPEG is a great file format, right? It's highly compressed. It's got good compression. It's got good image quality. But it's pretty expensive from a CPU standpoint to actually get it from the disk or from the wire if you're coming over HTTP, to get it into a form that we can actually do something with, right? We have all these steps, and all of those take CPU cycles to get there. So what we're doing now is to say, well, there's a point at which we actually have data that we can actually use in the GPUs. And that's if you're familiar with YCBCR format, or some people call it YUV, this is a luminance and chrominance representation. Most JPEG files are actually stored in this format. So what we're going to do is we're going to short circuit in WIC and give you a new interface where you can actually QI for an interface that says, give me the planar data, the luminance data, and the chrominance data. Now, in a lot of JPEG images, the chrominance data is actually subsampled, which means that you have one sample for every 4 pixels or one sample for every 2 pixels. And so rather than going through that expansion point, that chroma upscaling where we're going to blow out the size of that, you're not getting any new data, right? We're just duplicating the data to be able to put it into a form that the hardware can actually use. So now we're going to pull those off as 2 planar formats, get them into D2D bitmaps, and then run them into an image effect that you can use in the same places that you would have used the D2D bitmap. Reduces CPU time, and is going to reduce the amount of time, the amount of space that you're actually going to take on the CPU and GPU. So what we did is we did some analysis, and I'm not going to run through all the numbers, but you can take a quick look at them. These slides are going to be available. We basically looked at taking all of the images that were in the packages for some of our inbox apps in Windows 8, and we said if we expanded those JPEGs into RGBA, which is what we have to do today on Windows 8 to get them to use them, this is the sizes we would have. If we were to use those same images, didn't change the images at all, right? Just pulled them through the YCBCR effect instead, didn't do the upsampling, you notice that we would get, in most cases, about a 63% savings in memory usage. Now, the one that's interesting to look at is the weather app. You say, well, why is it only 25%? What happened? That's because the images that happen to be in that particular application are all high-quality JPEGs, and there is no subsampling. They're using, if you're familiar with the different nomenclatures for YCBCR, they're in 444 format, which means that every pixel in the compressed image is represented both in luminance and chroma. So we get the 25% savings because we don't have to add that alpha bit, which is always going to be 1 anyway in this case. Right? So at the very least, you're going to get 25% savings. But in most cases, if you have JPEGs that are in 422 or 420, you're going to see more of a 63% savings just by changing from using WIC and going out to a BGRA format to using the YCBCR effect. So the second one is block compressed formats. Now, this is a native format that's been around in DX hardware for a long time. There's actually 7 formats. They're related to different generations of graphics hardware. So the 3D crowd has known about these for a long time, but D2D has never actually taken advantage of them. BC 1 through 3 works as a block compressed format for 9 hardware. 10 hardware is 4 and 5, adds 4 and 5, 11 hardware adds 6 and 7. From a D2D perspective, here we go, no, there. We're just going to be focusing on BC 1 through 3, primarily because from a D2D perspective, we don't ask you to have to think about the feature levels like you do in D3D. And so introducing that concept here just makes life a little more challenging. So we're going to say, for now, we're just going to talk about BC 1 through 3. Because that means it doesn't matter which hardware you're on, you're going to be able to take advantage of this. So the block compressed formats are 4 to 8 bits per pixel, right? That's a lot smaller than 32 bits per pixel, which is what we're doing today. Gives you up to 87% savings in terms of memory relative to those RGBA images that you're going to pull in. It also maps very well from disk to GPU, such that we read it straight off disk and we push it straight to the GPU without any other conversion. It means that the representation on disk is a little bigger, actually can be compared to JPEGs. But again, it's going to be smaller than what you would have if you had a fully expanded image. Again, this is a lossy format, like in any other compression formats that we have out there. Most formats are. The difference with block compressed formats is there's not a lot of dials to turn in terms of what you get is what you get based on the way that the representation is. So my recommendation here is if you look at the block compressed formats as a way to be able to save space, you need to look at the images that you get out of the process. Some images look really great and you will know the difference. Others, there are certain characteristics that can cause you problems. And again, because it's a block compressed format, it needs to be multiple of 4 in both directions. You can pad those out. So let's look at what, just going to be a quick sort of highlight of what block compressed looks like. If we take an image like this and we look at a block, now the encoding actually is going to look at 4x4 blocks, so that's 16 pixels at a time. And from that 16 pixels, we're going to analyze that in the RGB space, and we're going to find 2 points that represent most accurately the range of data in those 16 pixels. And we're going to encode those as 565. So we already went from 32 bits to 16 bits for those 2 pixels, right? Those 2 values. And then we're going to linearly interpolate between them in RGB space so that we have 4 values. Then for those 16 pixels, using those 4 values, we're going to encode them, right, 2 bits per each one of those to get down to the final representation. Now, if you're looking at this, one of the things to note is if you have 3 discrete colors across that block of 16, you can't represent it in this accurately, right? But if you shift them over a little bit, maybe they line up, maybe they don't. So that's the place you're going to see, you potentially see artifacts. This block compressed format works really well for sort of smoothly varying kinds of images. It's not as, it can show artifacts when you have sharp edges depending on what the colors are and depending where they fall in the blocks. But again, it's a great compression format. So there's actually 3. I'm not going to spend a whole lot of time here, but just to give you a little bit of highlight of what the differences are between 1 and 3. BC1, think of it as if you have no alpha in your original data, or you just have fully transparent and fully opaque and nothing in between. BC1 is your friend. BC2 and BC3 have alpha. BC2 is better for alpha when it's not correlated, which means it's not smoothly translating. And BC3 is actually better for when you have correlated data. Again, there's a great reference at the end of the deck for a description on MSDN that talks about the block compressed formats. If you want to go read up on that, it's a great description that goes into a lot more detail than I can go into right now. So to look at how this works, we pulled one of the images from Cut the Rope, and this is the background image. Originally, when you think of it in the RGB format, when you pull it out and you expand it out, it's about 8 megabytes. Now, I'm sure you can't tell the difference on the slides given that we're projecting here, but notice the difference in size. 7.91 megabytes in memory versus less than a meg, right? Significant in terms of what we get. Just look at that again, all right? So we looked at all of the images that Cut the Rope had. If you just expand all of them out, there are about 200 megabytes of data that would show up in the CPU and GPU. If you use the block compressed formats, it's 35. 200 to 35, right? So when you want to think about how am I going to use my GPU resources, how am I going to utilize them such that I can get more things on the GPU and not have to page them out, this is one of the ways to do it. So let's look at, just give you sort of another look at what the performance differences are. Again, that's what this data is with that same image. This is it. We displayed this with IE. This is with IE10. This is without the YCBCR optimizations. So this is the time it took to decode the image on the CPU and the time it took for IE to be able to display that image. Here's BC1. Okay? Block compressed goes straight from disk to GPU, no translation, goes straight in. And it works natively in all the hardware. That means that I don't have to expand it. The hardware never expands it until it actually samples that pixel. And because it's a block compressed format, it's in a block, we can do that very efficiently on the GPU as well. So now you're thinking, well, how do I get block compressed formats, right? Because this isn't something that you probably have just laying around on your disk someplace that you've got block compressed formats. Well, Our recommendations are that you use your current existing authoring pipeline to generate the images that you use for your apps the same way you have been, right? Don't change the way you do that. Instead, there you go. Think about the compressed formats as being a runtime format, not unlike you might think about the other geometry things that you do, where you might model them with a given pipeline and then do a conversion step to get it into your app at the end. Same kind of thing. Think about this as a runtime format, author the way that you have been, and then generate them as a part of your build packaging steps. So again, this is not something that you want to think about from a user content standpoint. Don't think about trying to convert something that's you're coming over the wire on the fly to DDS and then use it in your app. Don't do that, right? The encoders are not fast enough that you're going to have the kind of performance. You're going to spend a lot more CPU cycles doing that encoding. Let the build steps do it. Think about it from the standpoint of it's going to be your app-specific assets that you're going to use as part of your package. So from an overall standpoint, think of it this way, right? Use the assets, create the assets the way you would, put them in JPEGs, put them in PNGs, whatever. Then use the tools, and I'm going to show you how to do that in just a second, and then run, at runtime, pull those directly into the GPU. So in VS, Visual Studio 2013, now has content pipeline that will allow you to generate block compressed formats natively as a part of your build steps. You can add the PNGs or the JPEGs directly to your package. You specify, so you're going to go into the general properties, you're going to specify that you want to use the content pipeline. That's a Boolean that says yes, no. And then you're going to say on this image content pipeline, you're going to say which compressed format you want. Note, you do need, if you're using alpha, Direct2D uses pre-multiplied alpha throughout the pipeline. That means you need to do this as well. It won't work if you don't specify that when you do the encoding, because it won't load. And then you just say the file name you want, and this will get built as a part of your package. It'll go into the package, and then you just can reference it directly and use WIC to load that DDS file. And there's some new interfaces off of the WIC, that WIC decoder that will get you those block compressed formats directly so that you don't have to do any decoding. So some quick advice in terms of how you want to think about JPEG versus DDS. If you've got JPEGs, if you're using JPEGs, you should be using YCBCR, right? It's not, you don't have to do any conversion in terms of the images that you already have. You should think about making the changes where you're doing your loading such that you can circumvent the need to go to RGBA images and use the YCBCR effects instead. It's going to give you somewhere between 25 and 63% working set savings over the RGBA data that you have today if you're using JPEGs. JPEG is definitely going to be a smaller footprint than it is for DDS, but it's not going to give you quite the same memory savings that you're going to get from DDS as well. For block compression, the DDS file format, think about these as your app local assets, right? These are things that you're going to use as a part of your build process. They work in my experience. The natural images, things that are sort of smoothly varying work. You won't see any artifacts. If you have kind of sharp edges in them, there would be some cases where you might see some blurriness. Again, depending on the size of the images and where you're using them, that will be noticeable as well. But you need to look at the images when you're using DDS. Again, 75 to 87% working set size savings over BGRA or RGBA images. So that's been a quick walk through the new things that we've added to D2D and our image stack for Windows 8.1. My recommendations are leverage the new features in 8.1. They're going to give you new performance in terms of color fonts. They're going to give you more fluidity in your applications because you're going to be using less CPU time and you're going to be using less memory such that your startup times are going to be faster as well. So here's the quick short list for you just to recap. Color fonts, use them for emoji, and my recommendation is start thinking about them for scalable UI elements as well. We're going to be talking a lot more at TypeCon in August about this particular color font technology, about how to build them and how to go about them. More information will be available in the next couple weeks. Our main font guy is on vacation, so he's going to publish in like another week or so. But I would highly recommend you look at color fonts as a way to be able to get scalability in your UI elements and be able to add color to them as well. Secondly, take advantage of geometry realizations where it makes sense. It can also significantly reduce the amount of CPU time that you take to be able to get geometry on the screen. And finally, evaluate the image compression formats. Use them to get better, faster load times, which will give you more accessibility to quicker load times and better performance and better utilization of your resources overall, which means you can actually use you can get more stuff on the GPU because you're not using as much space for the stuff that you already have. With that, here's the list of things that I showed you today. The color font sample is available on MSDN. The geometry realization sample is available. Now, the color font demo that I showed you includes fonts that are not included. So like all of the fonts from some of the other font foundries are not a part of that because we don't have rights to redistribute those. I mentioned the fill modes enumeration. That's also there. And then references. We have 2 new samples that are on both using block compressed image sample for DDS and the YUV work. And then finally, there's a write-up on block compression on MSDN that's been available. It's also there. Other related talks within the DirectX stack. These are other things that are going on. I had some questions earlier about the tiled resources one, which is 4-063, because a couple of people had asked me about that earlier. So, and with that, please fill out the evaluations. And I thank you for your time and attention. I'll be glad to take questions now. Yeah, and if you could, thanks, thank you. And if you could use the microphones, I'd appreciate that, so everybody can hear the questions.
So I have a question. So I have a question about the Surface RT. It supports like version 9.1 or something in DirectX.
Yes.
And if you want to use the shader things and such is the new version of Windows 8.1 going to allow the Surface to utilize these new features like this? Or?
Yes. All of these things that we talked about today work on Surface RT just as well as any other platform.
Okay.
Will these APIs degrade gracefully for backwards compatibility?
They are only available the new ones are only available in 8.1 and beyond. So they're not available on 8 or 7.
Okay, so when the app runs on 7, what happens?
So which APIs in particular would you be interested in? So the QI, so all of the image compression things are QIs off of existing codecs, which means that you need to be prepared for those QIs to fail. So from a WIC perspective, all of those you could build them down level, but they would not run down level. So it means the QI would fail, and you'd need to fall back to a pre-existing path.
Okay, thanks.
For geometry realizations, those are only available in 8.1.
Okay.
Okay.
So I'll be testing for version at runtime.
Yes.
Okay.
Is there any fallback to using the colored icons to even just get a single colored icon or a single colored glyph?
Well, single color glyphs are already supported, right? So you specify, when you draw text, you specify color. This new color technology actually allows you to have multiple colors within the same glyph.
Right, so if the colored glyph support is not supported, say it is running
right.
on Win 7, still pass color, it doesn't matter. Is it going to draw in black and white, or
That's
do
correct.
I have to detect?
Yeah, it will draw in black and white,
Excellent.
right? And you can, and If you don't do that translate, or you say, I don't want color, then the base level glyph, or think of it as the grayscale glyph, is still there and will actually be rendered. So if you don't do that translate or you don't turn on that flag, then you're just going to get the black and white version.
Thank you.
My question regards the Lorenz transform demo that you
Yes.
showed. I thought that was got that big speed up in Windows 8 for the TIR feature in DirectX 11.1.
That's correct.
So what is it in Windows 8.1 that's new in that
So
demo? That's
those
faster?
aren't 11.1 that's not 11.1 hardware. That's 11 hardware, right?
So that was 11 versus 11.1 hardware.
Correct. So TIR is only available in 11.1 hardware and beyond.
Okay, so yeah, I got it.
And so we did a bunch of work in the geometry paths, in particular in stroke performance, to make that much more to increase the performance by changing the ways that we're actually doing the tessellation.
But is that a change in Windows 8.1, or are you showing simply something that's a change in DirectX 11.1, which is already available in Windows 8?
So the TIR was 8.1 versus 8 on exactly the same hardware, which neither of them has TIR.
Oh, so that was non-TIR.
That was
hardware
non-TIR.
that was still rendering that demo.
Yes.
Okay,
Correct.
Thank you. So
Yes.
that's
So we
okay.
went from like 1 frame a second to 60
Okay.
frames a second.
Okay. So that was
on non-TIR hardware.
non-TIR
Yes.
hardware. Okay,
Exactly.
thank you.
Hi.
Hi.
You mentioned commandless. Now, that was a feature that wasn't widely adopted or supported by hardware.
I'm sorry, which one?
Commandless.
Yes.
So GPU vendors didn't support that, completely, right?
Oh, okay. So commandless from a D2D commandless.
That was
so
D2D commandless.
D2D
not
commandless, not
commandless.
D3D commandless. Sorry,
Okay.
I'm sorry, I didn't clarify that. Yes.
All right, thank
Completely different technology, by the way. Yeah.
We're trying to do large fonts, like screen size fonts, right?
Yeah.
And do you guys use geometry realization for large size fonts, or would that still be, what you currently were showing right now?
When we actually draw text, there's a point at which we go from drawing glyphs, which are small bitmaps, to actually doing outlines. And I don't remember exactly the point size at which that happens. That does not currently use geometry realizations.
So if I were to use large size fonts, I would still have anti-aliasing problems.
No. You will not.
Okay.
We'll do the rendering with geometry, it's just that we're not using geometry realizations to do it.
Got it.
Does that make sense?
Another question about the geometry realization. So when I do lines and things like those, can I define shaders to define patterns like dot, 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 dash, dot?
You can't define shaders with D2D. You can specify that you want to texture them, so you can apply gradients to them. You can apply any of the brush forms that are available in D2D.
So I don't have control over, is there going to be any way to control the tessellation and say, here is how I want these lines tessellated, or?
No. So the tessellation is all done by D2D for you. And it's based on, I didn't get into it, but there's basically a tolerance factor that you need to specify that tells you how close the realization needs to be relative to the actual geometric definition of that curve.
Okay, I have two more.
Sure.
So we've been having problems. We tried using D2D with D3D surfaces, and we had problems using depth.
You're using D3D surface, that's fine. D2D is built on top of D3D, so that's fine.
So there should be no problems mixing the two.
So you just need to make sure you do a begin end. Mm-hmm. So you do begin, do all your 2D stuff, then say end, then you can do your 3D stuff. But don't do 3D stuff in the middle of your 2D stuff. Right. Between the begin and end, that will be bad news.
And the new thing that you talked about, where you can create DDS files from PNGs, from your texture image resources. Is there a way to say, here is 10 PNGs, create one Atlas DDS kind of thing? Or is it
not with the tools that are here, no.
But there are custom tools that's there in the 2013 dev kit or something?
I don't know of anything in VS 2013 that will create atlases for you.
Okay. All right. Thanks.
Sure. Yeah. DirectX. Well, DirectX is an umbrella for a whole series of APIs, right? So there's D through D11, which is an API set which has feature levels associated with which are tied to hardware generations. Then there's D2D, which is basically version associated with the OS. It's just D2D. And there's D-Write and there's WIC, and so we think of them as they're packaged with the OS, they come with the OS. Pretty much, yeah. And we kind of talk about 11.2 kind of sort of, but there's no feature level 11.2 as an example. Yeah. Yes, sir.
These image compression performance improvements, have they been implemented in XAML? Do you know that? Or is there any way to access them?
Those two particular things are not available in XAML today. No. Sorry. Other questions? All right, with that, I thank you for your attention.